Department of Physics, which was established in 1958, presents St. Joseph's massive open online courses on the topic optics as skill effective course. Myself, Dr. C.H. Praveen Babu, Assistant Professor, Department of Physics, St. Joseph's College for Women Autonomous, Vishakhapatnam, Andhra Pradesh, India, as a skill effective course on the topic optics. The subtopic is Chapter 4 Polarization. Chapter 4.3 Malus Law and Nicol's Prism. Learning outcomes from this topic: understand and articulate what Malus Law states, understand the principle of polarization, identify the materials used, differentiate between types of polarizer. Malus Law. In 1809, Malus discovered a law regarding the intensity of light transmitted by the analyzer. According to Malus, when completely a plane polarized beam is incident on the analyzer, the intensity of polarized light transmitted through the analyzer varies as the square of the cosine of the angle between the plane of transmission of the analyzer and the plane polarizer. This law holds good for the combination of reflecting surfaces, polarizing and analyzing thermal crystals, Nicol's prism, etc., but fails when the light not completely plane polarized. To prove this, let OP is equal to A with the amplitude of incident plane polarized light from a polarizer and theta the angle between the plane polarizer and the analyzer. The amplitude of incident plane polarized light can be resolved into two components: one parallel to the plane of transmission of analyzer as A cos theta and the other perpendicular to it as A sin theta. The component A cos theta transmitted through the analyzer intensity of transmitted light through analyzer I theta is equal to A cos theta whole square, that is equal to A square cos square theta, since intensity is directly proportional to amplitude square. If I be the intensity of incident polarized light, then I is equal to A square. I theta is equal to I cos square theta. I theta is directly proportional to cos square theta. When theta is equal to 0, that is, the two planes are parallel, I theta is equal to 1 as cos theta is equal to 1. When theta is equal to pi by 2, that is, the two planes are perpendicular, I theta is equal to 0. The above results are experimentally observed in the case of two tourmaline crystals. Examples of Malus law in everyday life: polarized sunglasses, window pans of train and aeroplanes, photographic camera, 3D movies to eliminate dazzle from the headlights of cars and buses, etc. Nicol's prism. Principle. Nicol's prism is a device for producing and analyzing a plane polarized light. We know that when an ordinary light is transmitted through calcite crystal, It splits in ordinary and extraordinary beams, which are completely plane polarized with vibrations in two mutually perpendicular planes. If by some means one beam is eliminated, then the emergent beam from calcite crystal will be plane polarized light. In 1828, Nicol eliminated the ordinary beam by utilizing the phenomenon of total reflection at thin film of Canada balsam separating the two pieces of calcite. This device is known as Nicol's prism. Construction. As shown in the figure, a calcite crystal whose length is 3 times as its width is taken. The end faces of this crystal are grounded in such a way that the angles in the principal section becomes 68 degrees and 112 degrees instead of 71 degrees and 109 degrees. This is done due increase the field of view. The crystal is cut in two pieces by plane perpendicular to the principal section as well as the end faces PR and QS. The two cut surfaces are grounded and polished optically flat and then cemented together by Canada balsam. The refractive index of Canada balsam lies between the refractive index for the ordinary and extraordinary ray for calcite. For sodium D lines, the values are given below. Refractive index for ordinary mu naught is equal to 1.658. Refractive index for Canada balsam mu is equal to 1.55. Refractive index for extraordinary ray mu E is equal to 1.486. From these values, it is clear that the refractive index value for Canada balsam lies between the ordinary and extraordinary rays. Action. As shown in the figure, when a beam of light AB enters the faces PR in direction parallel to the long side, it is doubly refracted into ordinary plane polarized beam in the direction BO and extraordinary plane polarized beam in the direction BE, which was clearly shown in the figure. From the values of refractive indices given above, it is clear that Canada balsam acts as a rarer medium for an ordinary ray and denser medium for extraordinary ray. Moreover, the dimensions of the crystal are so chosen that the angle of incidence of ordinary ray at the calcite balsam surface becomes greater than the corresponding critical angle 69 degrees. Under these conditions, the ordinary ray is completely reflected at Canada balsam surface and is absorbed by the tube containing the Nicol's prism. The extraordinary ray is not totally reflected because it is traveling from a rarer medium to a denser medium and is thus transmitted with no appreciable loss in intensity. It is slightly displaced laterally but emerges out of the prism parallel to its original direction. Thus, only the extraordinary ray is transmitted. Since extraordinary ray is plane polarized, having vibrations parallel to the principal plane, the light emerging from the Nicol's prism is plane polarized as shown in the above figure. Limitations of Nicol's prism. It should be noted that the Nicol's prism acts as a polarizing device effectively with a slightly convergent or slightly divergent beam of light. If the incident beam makes an angle much smaller than angle RBA with phase PR, the ordinary ray will strike the calcite balsam layer at an angle less than critical angle 69 degrees. It is now not reflected but transmitted through the prism. In this position, both ordinary and extraordinary rays are transmitted through the prism. It is found that the angle of incidence on phase PR is limited to ABS dash, which is nearly 14 degrees. The extraordinary ray has also a limit beyond which it is totally internally reflected by Canada balsam surface. If the incident beam makes an angle greater than angle RPA with phase PR, the extraordinary ray will be refract more and more parallel to the optic axis, and its refractive index will approach to the value of mu 0. In this case, the extraordinary ray will also suffer total reflection. Now, no light will emerge out of the prism. Hence, to obtain plane polarized light, the incident beam should be confined with an angle of 14 degrees on either sides of AB. Uses of Nicol's prism. Nicol's prism can be used as both polarizer and as an analyzer. When two Nicols are arranged coaxially as shown in the figure, the first Nicol will produce plane polarized light is known as polarizer, while the second, which analyzes the polarized light, is known as analyser. When the two Nicols are placed with their principal sections parallel to each other as shown in the figure A, then the extraordinary ray transmitted by one is freely transmitted by the other. If the second prism is gradually rotated, then the intensity of extraordinary ray gradually decreases, and when the two Nicols are at right angles to each other as shown in the figure B, that is, they are in crossed position, no light comes from the second prism. This is due to the fact that when the polarized extraordinary ray enters the second Nicol's prism, it acts as ordinary ray and is totally internally reflected. Therefore, the first Nicol prism N1 produces plane polarized light and the second Nicol's prism N2 detects it. From this chapter 4.3 Malus Law and Nicol's prism, what have we learned? How the detection of polarized light be done, the working mechanism of Nicol's prism, the concepts in optical instruments, uses of Nicol's prism.